Okay, so let me remind you where we stopped. So we were talking about integrable representations, and these were where so we had our Chevalier generators xi, yi, hi, and let me be careful by putting these indices there. Okay, and so we need the hi's to act diagonally. Okay, so the eigenvalues of hi, so hi from 0 to n, so then the eigenvalues are usually denoted, let's say mu I equal to 0 to n, and these are n tuples of integers, and then the xi's and the yi's have to act locally nilpotently. And then we defined, so if you give me a mu, again, so let's be careful. So let me write this as underline mu, as mu naught up to mu n. And these are non-negative integers. The other way. Okay. Then one can define canonically a representation V mu of the affine Lie algebra G hat, mu underline, okay, such that, which will be generated. So let me just use all this usual language. It will be generated as a module for the universal enveloping algebra of G hat by an element V, which will satisfy the conditions that HIV is mu IV, XIV is 0, and YI raised to mu I plus 1V equal to 0. And this is for all I equal to 0 up to n. Then the fact is that if you look at the subalgebra generated by xi, yi, hi, with just I equal to 1 to n, right? So the subalgebra of G hat. So this is just isomorphic to G, okay? And what is true is that if I now write mu equal to mu1 up to mu n, then this is again a collection of non-negative integers, therefore, right? This defines a highest weight, so a finite dimensional representation for G, which we can call V mu, okay? So the fact is that V mu is included. So this V mu underline is a module for G hat. So we can regard it also as a module for the subalgebra, right? So we have an inclusion of V mu in V mu hat, in V mu, as G modules. Okay? But this space is this space is infinite dimensional, whereas this is finite dimensional. So there are many more G components. So V mu is equal to direct sum V nu. Okay? These are G modules, but there are very many of them with multiplicity. Yeah. Mm-hmm.
N plus 1 there, mu 1. Mu 1. Z plus n plus 1.
Ah, yeah. Yeah. There are n plus 1 integers. Okay. So this is so this module is a huge infinite dimensional space, but it contains a canonical copy of the module for G, and it contains with multiplicity 1. Okay. Okay, so having cleared that up, so now today I just want to talk about, and all these modules had positive level. So the center acts on V mu by a positive integer unless it's a trivial module. Okay. If mu is not equal to 0, if mu is 0, then it's a trivial module. Okay. So now we want to talk about level 0 modules, which in some sense, depending on your view, we should have talked about first, okay, because they're the easiest to construct. So we're trying to construct modules for LG. So this is where the center acts trivially. So this means it's a representation of, means we're looking at representations of LG. Okay. So here you have two objects whose representation theory you know. G is a simple Lie algebra. You understand all its irreducible finite dimensional representations. L is a polynomial ring in one variable, and it's a PID, and you do that in the first course in algebra, understand all its modules. So you should be able to glue the two together to produce representations of LG, okay? And this is, so what is the most canonical, so what is an irreducible representation of G? I've just told you. It's given by integers V mu, where mu is in Z plus N, okay, non-negative integers, irreducible finite dimensional. What are irreducible representations of the Laurent polynomial ring? Well, those are just quotients by maximal ideals, right, one-dimensional modules. So these are given by the evaluation map. So you glue the two together. So now what do I take? I take an element X tensor F in my loop algebra, and I make it act on an element V. So I'm going to just define an action on V mu. So this V is going to be in V mu. And what do? I've taken a fixed representation there. So I just evaluate F at A, and then I do XV. So it's a completely obvious, trivial thing to do. And then you just check. I mean, this is not a hard checking. It will just use the fact that this is a map of Lie algebras and this is a homomorphism of rings. Okay? So it's simple checking that this is a Lie algebra, that this is a module for LG. Okay? And so we need to give this module a name. So let's call this. So this module depends not only on the choice of integers that I've taken, but also on this parameter, right? So of course you have to prove a little result, which says that V. So I mean, if I want to put this dependence on the parameter, it should have meaning, right? So it must mean that V mu A. Otherwise, why bother with the parameter? Is not isomorphic to V nu B if A is not equal to B and mu is not equal to B. Okay. So these parameters really are important. They are not, all these representations are non-isomorphic representations. Now the existence of indecomposable representations is then completely obvious also, because of course this principal ideal domain has irreducible representations, but it has plenty of indecomposable representations. You replace this maximal ideal by a power of a maximal ideal, right? So it's a trivial construction.
The decomposition of V bar as G modules. Is there a description of the lattice points that appear in there?
You mean a precise description? In general, no. These modules are too big. So yeah, you're talking about branching rules for this, right? You take V mu and you want to know what kinds of things. Yeah, no, you can make some general statements, but yeah. So, I mean, so these modules are sort of quite hard to work with. Typically, the only case where you know any concrete things is where mu on the center is 1. Those are called the basic representations. Because when you demand that mu in the center is 1, you're essentially looking at some fundamental weight, right? Because mu is equal to mu1 plus. So only one of the integers is non-zero, and that integer happens to be 1. So that's essentially the only thing that's getting studied. But after that, if you go beyond this center being 1, the modules are very difficult. So one doesn't know very much about them, about this. I mean, one has to always be careful what one means by one doesn't know very much about them, but one doesn't know the answer to the kind of question that you're asking. Okay, so going back to this, so then if you take G tensor CTT inverse, so if you take LG and you look at the and you take the module V tensor, this. So I don't want to, modulo T minus A raised to M, okay, M greater than, so then this is an indecomposable, reducible representation. if m is bigger than 1. Simply because as a representation of CTT inverse, it's indecomposable. Okay. So we have a bunch of representations, and you can always hope you've got them all. Okay. Okay, so how does one see if, so before you start trying to prove that these are all the representations, you need to know that you need to know whether this fact is remotely likely to be true, right? So what is the standard way to construct representations, new representations from new old ones? You just take tensor products and see if they give you anything new, right? That's what you always do for groups, and you do the same thing here. So if you look at, so then there's an exercise which is not very hard to do. So if you take, let's just think of it for SL2 for the moment because it's easier to write down. So if you take V, it's not important. If you take V mu A, okay, tensor, let's say V nu B, then you can prove that this tensor product is irreducible if A is not equal to B. Okay. Basically, so roughly speaking, it's because if you look at CTT inverse and you go modulo the ideal T minus A, T minus B with A not equal to B, then it breaks up as a direct sum. So everything is being controlled by this thing, right? So it's A not equal to B. And of course, if A equal to B, we got a indecomposable representation. Okay. So obviously these are not all, and then the theorem one wants to prove is then kind of clear. If you can do two things, you should be able to do an arbitrary number of tensor products, right? Yeah, so I think I don't want to see how to prove this. We'll be here till tomorrow. So the theorem is that any irreducible representation can be written as a tensor product of representations of this form. So here I've written it for SL2. The thing in general is clear. Okay? One way, if this theorem is relatively straightforward, to show that this tensor product is irreducible is straightforward. You have to work a bit more to prove it the other way. Okay. Okay. And so as long as your parameters are all distinct, A1 up to AK being the parameters, you're in good shape, okay, for the same reason that I told you over here. Okay. So this way of writing this classification is very explicit, right? If you know all the G modules and now you're just sticking in some parameters and taking the tensor product. So it's nice and explicit, and it sort of slows you down a bit because you don't quite know where to go from there. And this index set is really a very unpleasant way of writing it, right? I mean, you want a nice compact way of describing the index set to make any sense with. So I mean, I really think notation is half the challenge in doing mathematics. You set it up right, especially when you're doing algebra, and then you can do many things. So this index set is wrong, and so a better way to do it is the following. So what do we really have here? So for every integer, I have a scalar, right? So I'll start with my integer 1, okay? And so the index set is actually in one-to-one correspondence between with the following monoid, okay? So you take the free abelian monoid generated by this element omega 1a. I just give myself an element omega 1a. 1 represents my SL2, and A represents my parameter A and C star, okay? So this is a huge group, huge monoid, and this theorem can be reformulated, if you like, by saying that there's a one-to-one correspondence between the elements of P plus and the irreducible representations of the affine Lie algebra. So what I'm doing over here is, so if I look at this, so what do I want to, so I have to assign an index to this. So so the parameter is A1, and then I want to make this N1 reflect itself, and so I put it here. And then here I want to take A2 and N2, so I do it there, okay? And obviously I want to take, and obviously when I'm writing it over here and I'm taking powers, I mean A1, A2, AK are distinct. Otherwise, why would I write them separately, right? So this is a sort of more compact way of writing it. And now, of course, you have to do this. This I've written for SL2. But if you were doing it in general, well, then what would you do? Yeah, free abelian monoid, yeah. Yeah, I didn't write that. Yeah. Okay, and so now if I was doing a higher rank, what would I do? Well, so this 1 represented the rank of SL2. So in general, if I take 1n, right, then I would give myself, if n was the rank of my Lie algebra, then I would give myself, what's it called? An omega for every index of every node of the Dynkin diagram and every a. So this will be I in 1n and a in C star. Okay. And then the exercise that a student should do is what is the module you would, so if I gave you something like this, so this is a huge mess to write. So supposing I took an element, so I'm not going to write it. So supposing I took an element omega of this monoid, right? I write it out in terms of these generators, yeah? What is V omega? What is the irreducible representation, irreducible tensor product that it corresponds to? Because I told you that every representation is a tensor product of these representations V mu I A I. So you should be able to and here and here I reconstructed it for you for SL2. So then the exercise is to just reconstruct in this language for higher rank. Okay. Okay. So once you ask this kind of question, we know we have, so we have all our irreducible representations. And then we've seen that we can get indecomposable ones in a very natural way by just taking indecomposable representations of the loop algebra of the Laurent polynomial ring. So then what do we do next? So, yeah. So these are the questions that people were asking. So when you're doing representation theory, you very often have other modules with the same index set, right? When the category is not semi-simple. So that's what you try to do next. So you look back again. And then, so when we were doing these algebras in symmetric groups in characteristic P, so you had these irreducible modules given by Young diagrams. And then you have the spect modules, which were much bigger, right? But they're indexed by the same data, okay? And they had all these nice universal properties. So you think, well, maybe that's what you should try to do, right? So instead of, so I should say that there's a gap of maybe 25 years between the time one classified irreducible representations and thought about this indecomposable representation. So you've sort of come to it in strange ways. But anyway, so you want to also define, so you want to define some kind of universal modules exactly like they did. So you want to define the analogs of spect modules, okay? Now, in the characteristic P, you didn't have to do any analogs because you just reduced mod P. You took a Z lattice, went mod P, and you got them for free. But here you have to somehow come up with a definition, okay? So, okay, but now we have a well-defined problem, right? We want to know if I give you an element of my monoid, do you have an indecomposable representation associated with it canonically, which has nice universal properties? And the question is, how do you construct them, right? So again, you go back to your basics, right, to whatever you learned and still store in your memory, which is that when you're doing finite dimensional representations, you also, along with classifying them, you give a presentation of them, which I've written a few times already, right, so these representations of V mu. And I've never talked about presentations of irreducible modules. It seems unnecessary, right? That's perhaps one reason for the gap. It just seemed so unnecessary because you could describe them so explicitly, tensor product of well-known things. So you know everything about it. You can multiply their characters. The characters of irreducible representations are given by wild character formulas. So it seemed terribly boring. So one never worried about the presentation, but really one should have, okay? Okay. So sometimes things being very explicit and easy to understand holds you back in sort of pursuing the subject further, okay? So now I want to talk about, so supposing I decided that I wanted to prove my presentation anyway. So now I've decided it's an interesting problem. How do I find out what the relations should be? Well, how do I make a guess for the relations? So always you want to put the minimal possible conditions, right, on the generators, because otherwise you have too many things to check. So you look at, so if you look at, so for Vn, so again I'm just doing SL2, but it's not important. So if you're doing Vn, then we know that you have the relation xv equal to 0, hv equal to nv, and y to the n plus 1v equal to 0. And now what have I done? I've just given myself an extra parameter, Vna, right? And when I look at it, I still have xv equal to 0, okay? But now I have something slightly different here. I have that h tensor t minus a power r on v is always 0, right? R not equal to 0. Because I'm substituting t equal to a, so this becomes 0, and hv equal to nv. Right? I'm always putting in this minimal possible relations that I can see, and I keep that one, which is just y to the n plus 1v equal to 0. So these relations obviously hold. I don't want to put in any more because I want to see how minimal I can keep them. And then the question is, what does this define? Does this give a presentation of Vna? Or is it bigger? So that's the question on us. And of course, since I built this module by looking at the relations that held over here, this is obviously a quotient, right? And so now the question is it isomorphic? And the answer is no. I see, I've got some error over here. Okay.
Condition y plus 1 v is equal to 0. Wouldn't that imply that y tensor t is to r n plus b?
So, sorry, say that again?
So this
Y tensor t.
t power r n is one of your conditions.
Yeah.
So, but y is n plus 1 v is, y is the important, I mean.
Yeah.
And that wouldn't, it is this sufficient condition for the whole loop will act as
It might be, but yeah. It might, yeah. But so you see, in my definition, I didn't use it. I didn't put it finally in my definition of the local while module. Because it implies it, yeah. I don't need that, yeah. All those things that need lot of proof, but. Yeah. Okay. So. Yeah. Okay. So now the question is this bigger? And the answer to that is yes. Okay. So it's a small example, small exercise. So which I'm not going to do, which is that. So how do you know that the answer is no? So if n equal to 1, the answer is yes. Okay. Because you just calculate that, let me give this module a name. So I want to call this module now WNA, okay. So this is the module generated by an element V with all these relations. So if n equal to 1, one can just check that the dimension of W1A is equal to 2, equal to the dimension of V1A. This is a very small module, so you can do all calculations by hand. If you take n equal to 2, then you'll find that you can prove that dimension of W2A is equal to 4, not equal to the dimension of V2A, which is equal to 3. And the only way you can prove this is by constructing a specific example. Or you could just, actually, in this case, you could just look at this, my favorite example, which is V1. No, I'm not going to commit myself to that. So you can, it's just a small example that you have to consider. So basically what you do is you prove that there's a short exact sequence which will look like this. So it's a calculation of X that you have to do. And it's not so you have to actually compute that, but it's not a hard calculation. Okay, so then you know that you've got this modules done. So then, yeah, so that's as much as I'm going to say about that. And now we have a perfectly good, so now what I've achieved my goal, which is for every omega, well, I've partially achieved my goal, which is that for every omega in my free abelian monoid, I have now two modules. One I've called W omega and one I've called V omega. And I have a and I have that property, okay? So for those of you who know Verma modules, now this looks like the Verma module M lambda for semi-simple algebras, okay, which you know maps onto the irreducible module V lambda. Okay. So, yeah. So here I've so actually I've told a bit of a lie here. So because here all I've done is told you how to define WNA, right? So I haven't told you how to define it for an arbitrary element omega, right? So what would I guess? So if I took W equal to W1A1 raised to N1, W1AK raised to NK. So what would I want to guess for this module? Okay. So I would just want to take the tensor product, right? So of W N1A1 tensor WNK AK. But then what would so I've got a module defined, but then what would I want for it? I would want to know that this has the same universal property, right? So I would want to know a presentation for it. So this has a universal property by definition because I gave you a presentation. But when I take the tensor product, it's not so clear. So that's an exercise. Okay, so we take this W omega to be that. And then the theorem is that, in fact, if you define W omega in this way, then it has a presentation given by that. So you see, so you have a single vector generating this W omega. Here, since I'm in SL2, X tensor 1 of V is 0, this relation didn't change. Well, it changed because I have N1, N2, Nk coming from here. So the correct power of Y has to be 0. So that changed. And this relation here changed. I just put in all the parameters to make it change. So that's a theorem that one has to prove. And it's, yeah, so all these theorems sort of, they're natural when you think about it, when you split it up, and they require some work to prove it. But okay. Then you have to ask yourself, what kind of module have you constructed? So far, I've always been talking about integrable modules. So at a minimum, I want it to be integrable, right? And all my examples showed me that these Weil modules were finite dimensional. So then the next result you prove is that it's a finite dimensional module, and the universal properties guarantee that it's a unique irreducible quotient. Okay. So now we have finite dimensional modules. You have, once you start with this kind of thing, constructing modules, you have canonical questions that you ask. What is the character of the module? What is the dimension of the module? And perhaps most importantly, is this module interesting in any way? I mean, just because you can construct it and it looks similar to other things, is it connected with anything else in the literature? Okay. So, yeah, so I want to address some of these questions. And so these questions are on dimensions and characters and so on, and that took a long time to prove. So there were various people involved in the proof of these things. But so let's just look at a little bit of the history. So these Weil modules, W omega, we originally defined with Presley in 2000. Okay. And then we had a conjecture for the dimension of this Weil module. Okay. So I've written this conjecture for general G. Okay. So I'm taking this omega, this I1, A1, IK, AK, right? I don't know why I wrote S1 there. I should have written A1. So, so this is, here the A's need not be distinct, right? Because the things are repeating, the nodes are repeating, and I haven't said anything about the nodes not, the nodes are not repeating. So I could have something like, so this goes back to the exercise I talked about. I could have something like V1, omega 1A and omega 2A if I'm working in SL3, for instance. So here I'm not insisting that the parameters be distinct, okay? So they can glue together. But what this statement conjecture is telling you is that if I want to know the dimension of this module, I just have to take the product of the dimensions of these sort of just a single omega. Okay. So in this case, the dimension of this module would just be the product of the dimensions of W omega 1A and then the dimension of W omega 2A. Okay. So that was what the conjecture was. We proved the conjecture for SL2. And then, of course, what's the use of this conjecture if you don't know the dimension of these fundamental modules, right? So for SLn plus 1, one knows exactly what they are. It's just a dimension of the underlying irreducible module. So the while module is not on the fundamental weight. So for a single node, it's not interesting. This is like, as I said in the case of SL2, I told you that dimension of W1A is equal to 2 equal to dimension of V1A. Right? So this is just a generalization of that. Okay? But what is interesting now is that this statement is false in other types. Okay? And this can be, and so in fact the dimension is strictly bigger. And yeah, so I had a theorem which told you what this dimension was. Okay, but so this fact is really what makes it interesting, because in some sense these modules all came from looking at representations of quantum affine algebras which are connected with physics in some way. And Kirillov and Reshetikhin, both math physicists, conjectured that we had these kinds of modules. Okay. I don't know where the pointer's gone. Ah, there it is. Okay. They conjectured that you have these kinds of modules. They call them, these are sort of called fundamental Kirillov-Reshetikhin modules. And they told you all kinds of things about its dimension and things like that. Okay. So this immediately became, if you like, so I came to the subject from there, but if you like, this is a justification for the interest that it connects up with things that other people in a completely different area were interested in. Okay, so this was quite a funky fact, and the structure becomes quite complicated as you change your algebra and you change the rank, but we still know what the dimension is. Okay, so this conjecture took forever to prove. We proved it for SL2, then I proved it with Loktev for SLn plus 1. And then Fourier-Littleman proved it for simply laced, and then eventually it was settled in 2010 for the non-simply laced case by Naoi in Japan. Okay. So as I said, I started studying these things because they came from that subject. But once you start studying something, then new connections sort of begin to develop. And then there's more reasons to study them. Okay, so as I said, so once you know the dimension, the next thing you're kind of often interested in is what is the character of the representation. And it turned out that the character of these modules are really specializations, very particular specializations of Macdonald polynomials. Okay, so Macdonald polynomials are sort of a family of symmetric functions. Okay, and this connection with symmetric functions and representation theory is also old. Right? It goes back to, in the case of GLN and finite dimensional representations, the character is given by the Schur functions. So it's a very old connection. So and now these modules again have this nice property that the The connection is not with something like Schur functions, more complicated objects, but because modules are more complicated, but they're the Macdonald polynomials. Okay? So this is one further reason why they're interesting. Okay? Are there any questions? Okay. So now I've got my local while modules, which play the role. So perhaps I should just say a little bit about so if you're working in a semi-simple so if you're working in sort of nice non-semi-simple categories, right? So typically you understand the simple objects in it. Okay. And then you have, so let's say you have an index set, let's call it I. And then very often, in many of the theories, representation theoretic things that you study, at least in Lie algebras and so on, you also have associated to it this universal object. And really, if when you're doing, you can't seriously study non-semi-simple categories if you don't have projective modules in them. So you need projective objects. Okay. So if you look at almost any form of representation theory, whether you're working with algebraic groups or whatever, in characteristic P, you'll always have. So they're not called universal, they're usually called standard or co-standard. So let me use that language because that's more standard. Okay. And the question is, how do you interpret them? So in the category O for semi-simple Lie algebras, you have your irreducible modules as your simple objects, you have the Verma modules as your standard objects, and you have projective modules. Okay. So I've got two of them, sort of. Oh, and then you want, and so you don't just want these things, right? You want these things to somehow be indexed by the same set. You want these things to somehow have a nice connection with each other, right? So if you call the simple objects V, and you call the standard objects M, and you call the projective objects P, right? So associated with some particular index thing, then you have. So let's say you take an element I here, so let's call this Vi, Mi, and Pi. Then you have a sequence of, what's it called, surjective maps, Vi. So this is called, this is actually a projective cover, which means it's sort of the smallest projective object. So if you have enough projectives in a category, then you can do serious homological algebra and so on. So what is a reciprocity theorem then? You don't always have reciprocity theorems, but when you do, they look. Okay, so I said we're working with, did I say we're working with nice semi-simple, so nice non-semi-simple categories. Okay. So what shall we mean by nice? So once your category has non-semi-simple things, you can talk about Jordan-Holder series. That's the approximation for semi-simplicity, right? So you want every object in your category. So every object in the category should have a finite Jordan-Holder series, or it should have a manageable, anyway, should have a Jordan-Holder series. Okay, so what that means is that if I take any W in my category, W is an object, then it has a decreasing sequence such that Wi modulo Wi plus 1 is irreducible. So it's isomorphic to some Vj, right, with J in my index set. So I shouldn't say, let me use R over here, so that I and J are reserved for that. So this is a Jordan-Holder series. And then one usually defines a number. So this Jordan-Holder series should be well defined in the sense that if I take another flat decreasing sequence of submodules like this, where the quotients are irreducible, I'm going to get exactly these up to permutation. Okay? So then I can define a nice number, which is W, the number of times an irreducible module occurs in this Jordan-Holder series. So you want this property. And again, all the good modules that show up in Lie theory, they also have the property that the projective modules have a flag by standard modules. So whose sections are standard modules. So that means if I have a P, then I have a decreasing sequence, P1, P2, PR. And I need PI, PR by PR plus 1 to be isomorphic to some standard module Mi. Okay. So every Verma module, for instance, has a Jordan-Holder series. Every projective module in the category O has a flag. It's called a flag by Verma modules. Okay. And then this is called, and then you can imagine, you want to prove, of course, you have to prove that this flag, no matter what flag you take, the Verma modules which appear in it are unique up to permutation. And then you have this number, P of Mj. Maybe let's call this Pi. Yeah, so P of Mj. Okay. So this kind of thing goes back a long way. It goes back to Brouwer and so on, who prove such results for different kinds of, maybe for finite dimensional associative algebras and so on. So variations of this continue to appear in the literature. Okay. Okay, so I've told you all this. So what is a reciprocity result? It tells you how, it sort of wants you to relate multiplicities of Jordan-Holder series with multiplicities of standard objects in projective things. So a standard kind of projective, standard kind of reciprocity is the following. So supposing I take a projective module, P, with index I, okay, and I take its flag, and then Verma flag or standard flag, and I ask you, what is the multiplicity of my standard this Mjth standard module in this projective module? Okay. How many times does it occur in a flag over here? Then one way to say that is that it's equal to Mj Mi to Vj. No, I think it's Mj to Vi. So you want to know this, and instead you calculate this. You calculate the Jordan-Holder series of Mj, and you calculate the multiplicity, and you say that those are equal. So this is one kind of reciprocity, and sometimes it doesn't work so nicely. So you do something slightly different, which is, so you have this, okay? And instead of exactly Mj, you sort of have to go to a quotient of Mj, which is Mj bar, and then it's still Vi, okay? So I think this is called Brouwer reciprocity. Anyway, so there are plenty of examples in representation theoretical literature of these kinds of reciprocities showing up. Okay. So, yeah, so of course then I want to do that as well, right? So, since I'm trying to borrow ideas, but then I ran into a big problem. I don't know what category to work in. I've always got finite dimensional modules, and I can prove that there are no projective modules in my finite dimensional category. So that was a sticking point for a long time, okay? And nobody believes you when you say a category doesn't have enough projectives. They think you're just doing it wrong, but it was actually true. So somehow I want a bigger category, but then what do I mean by bigger? Even for BGG reciprocity, we did go to a bigger category, which had infinite dimensional modules. Verma modules are infinite dimensional. So the question is, what does one mean by bigger? And that continued to be a problem, because then you can't prove if you're, we don't have Noetherian, enveloping algebras are not Noetherian, so then it's not clear that Jordan-Holder series exist, and so everything is continually a problem. Okay, so how did this problem then eventually get solved? It really got solved by looking at this. So when you're studying these local Weyl pointilles, you're trying to prove its character formulas and so on. So one of the things that came into play was that it's convenient, instead of working with this full loop algebra, G tensor CTT inverse, to work with its subalgebra G tensor CT. Okay? Now, every representation of G tensor CTT inverse is, of course, a representation of G tensor CT. But this algebra has one representation which you don't see over here, because here you cannot, just like this algebra has one more representation than this, here you can take t equal to 0, and here you cannot. And just that fact made life much more accessible, okay? So then we decided, so with my colleague Jacob Greenstein, we decided to start looking at representations of this algebra. This is called the current algebra, and it's not so arbitrary actually to look at it. This is actually so this is actually a parabolic subalgebra of my algebra. So it's a very canonical thing to do, to look at the canonical subalgebra to look at. Okay. So this extra ideal that you have is really useful, because it allows you to talk and construct graded representations of my algebra. And then I can insist that my graded, so you see, so what is a graded representation? So you take, so my Lie algebra, so G tensor CT, also G tensor CTT inverse, right? They're both graded by the integers. Right? So you can write them as a direct sum of vector spaces with rth graded piece. But this is only graded by non-negative integers. This is graded by the negative integers, okay? All integers. So now when I'm looking at representations of this V10, right? So I'm taking n in Z, okay? So I can look at graded representations of this or this, okay? But it's much easier to work with this, because these negative things make all my spaces infinite dimensional. Well, I can't control the grades so well when I'm working with that. So instead, one can just work with graded G tensor CT representations. Okay. And suddenly life becomes super pleasant, because now I can define a projective module. So I'll do it for SL2, okay? And I'll write down what the projective module is. So supposing I take Pn. So this is now a standard construction in Lie theory. I just take the universal enveloping algebra of G tensor CT, okay? And I tensor over G, UG, well, this is SL2, of the usual representation Vn. Okay? So this is going to be a huge representation, because here I'm taking U of SL2 tensor CT, and here I'm taking only U of SL2. So there are lots and lots of powers, okay? But it's a standard, so in relative homology, it's standard to see that this is a projective object. And in what category? So this is in the category of graded modules. But it has a very important restriction. It has finite dimensional graded pieces. If I worked with this algebra instead, G tensor CTT inverse, then that algebra has infinite dimensional graded pieces, right? Because supposing I could look at things like this, X tensor T power minus R, Y tensor T power R, for all R. All these things have grade 0, and they're linearly independent. So this is very unpleasant. There's no finiteness condition I can impose when I work with that. But when I work with my current algebra, I have canonical finite dimensional conditions too. So I do that, and then I've got my projective, and then I can prove my BGG reciprocity. So again, there is, so yeah. So now I want to prove my BGG reciprocity, and I want to prove that, so if I'm working with, so I'm hoping that my local while modules are going to do the trick. Okay. So these are also defined now at t equal to 0, so there is some small modification to be done. And I'm hoping to prove so W log M, and I'm hoping to prove that that looks like W log M Vn. Okay. This is what my canonical reciprocity would look like. But there's a problem. These are giant infinite dimensional modules. These are tiny finite dimensional modules. Okay. So this is the problem of this Brouwer reciprocity. So that's why I stated it over here. This module is sort of much bigger than this module. So I have to replace, so I really am looking, therefore I'm not going to be able to, so if I look at the Jordan-Holder series or the Verma flags, or the Jordan-Holder series will be okay, because this is a finite dimensional module. But because this is such a small thing, I'm not going to get finite multiplicity. So then I have to replace that by something called the global while module, which I don't want. So an appropriate replacement exists for W log N. Okay, so that's known as the global while module. So we take M to be this replacement. So let's call it W local. No, so W global N. And then this theorem, and then the theorem is that, so this was proved, I don't know, in 2015 or something in joint work with Ion and previously with some students, that Pn, and then if I take W global M, okay, so I'm trying to imitate this Brouwer reciprocity. This is equal to W log, so Wn, and then Vm. Wm Vm. Okay. So these were all reasons then to get into the representation theory of current algebras. But really you had to know that current algebra somehow came into play in the whole thing before you began to. So at every step you want to justify why you're doing something, right? So that you're not, so anyway, so that was the reciprocity result, and with that I'm done. Thank you. I'm sorry?
If you reduce it further to the current polynomial, you reduce Pn further to
I'm sorry.
You said that the parametric subalgebra.
Yeah.
So now reduce it further to G tensor CTT. Reduce Pn to.
So, I mean, if you induce it further, this will just become UG tensor CTT inverse. Yeah. And then you have problems. Yeah. So one doesn't know how to go further. Yeah. It just, you need some structure, some finiteness conditions, which are totally missing in this loop algebra picture. So, okay. So with that, thank you for your attention. Yeah, so these so in the case of SL2 or SLN, these are Koska polynomials. The multiplicity of this appearing in this is given by Koska. Yeah. And what is it? Yeah. Yeah, so in general, they're McDonald polynomials. So if you're working in arbitrary type, then they're specialized McDonald polynomials. One of them. The non-symmetric McDonald's evaluated at t equal to 0 or something, specialized correctly. Yeah. About loop groups, you mean? No, because I think the structure is very hard. I mean, defining smooth maps and things like that are very hard on this. So these kinds of things I don't think lift. Yeah, level 0 representations, yeah, I don't know. Yeah. People have studied the other kinds, lifting the other kinds, but generally doing analysis on these smooth infinite dimensional spaces, yeah, it's not for me. That's what all this is about.
But you can call that a tilting modules kind of.
Yeah, you can do tilting modules in this theory. So, yeah. So you see, you have these. So you have these what I call global while modules, right? And then you have these local while modules. So then you can ask for a module again indexed by the integer n, such that it has a filtration by these global while modules and another filtration by the dual local while modules. So usually tilting is the same thing coming in both places, but here you have to. Again, you have to interpolate it correctly. So it's by global and local, just like this reciprocity is global. And then you can prove that they exist, and yeah. So some of those things you can do. And they have nice character formula and so on. But again, now, so those things we defined, but it wasn't clear what applications they had later. So the combinatorics was sometimes interesting. But yeah, so there's lots of combinatorics associated with all this. All types, including twisted. And A2 and 2 and so on.
What about the representations for this parabolic? These are some you are given, but if one wants to only get this parabolic from algebra, ask for its representation.
Yeah, so you mean what are its irreducible representations? Yeah, well, you see, because it's graded, it essentially only has, so for CTT inverse, you had this V and A, right, where A was in C star. But here, because it's graded, the irreducible representations are just of this form, Vn. There's only one point. It's because there's only one point that you're able to shrink everything so much. So you have the irreducible representations, and they weren't very interesting here. They're even less interesting here, but the rest of the stuff becomes more interesting. So again, you never want to work with irreducibles. You always want to work with interesting indecomposables. And then so then you have to know what interesting means. So it comes from some other place again. So yeah. So I should say really that once you get to this kind of language, what you have is a very interesting connection with positive level modules. So this is kind of new because everybody always believed that the subjects were totally disjoint. But when you think of it this way, what happens is that because this is a parabolic subalgebra, so this is this connection with Desmesure modules. But so let me just briefly tell you that. So if you're doing, so we have a while group W, right, associated to G. So for SL2, it's just a symmetric group on two letters. So for SLN, this is Sn, okay, if G equal to SLN plus 1. Okay. And now if I take my irreducible representation V mu still for SLN plus 1, okay, then I can talk about V mu on W mu. Okay, so there's a while group action on the set of integers. Here this action is obvious. You're just permuting the for SLN plus 1 is just that. Okay, and this is a one-dimensional space. Okay, and you can look at the action of the Borel subalgebra, which is just in the case of SLN plus 1 upper triangular. You take upper triangular matrices and you look at its action on this one-dimensional space. Okay, so this is called a Desmesure module. It's not a module for all of G, it's only a module for the Borel, okay? Now you can do this for the affine Lie algebra, so we're in the context of positive level representations. So you take mu and Z plus N plus 1, and you can do this, sorry, I think they all have to go. Yeah, so you can do V mu of W mu again, okay? And then you have this, the analog of the Borel subalgebra, and you can do that. That's called a Desmesure module, okay? And if you choose W carefully, then what you get is precisely the local while. So if you choose W carefully and you choose mu carefully, maybe mu of level, then you get the local while module for GT. So there's a nice link between the representation theory of the current algebra, level 0 representations, and the positive level representations.
See how you got the character formula?
Yeah. So people had, yeah. So once you make this identification, people had calculated this character formula as coming from the Koska polynomial or the McDonald polynomial. Yeah. Okay. So there are all these interplays, and then you borrow from all subjects. Okay. Okay. So I know they have to go. So maybe you guys should go since you have. Okay.
So is there any geometric realization of this local well models?
Yeah, I'm not the right person to ask, but yes, I think they can be realized geometrically, but not as sections of line bundles like you guys like to do. But I think there's this. Yeah, I think, but I don't know how to do them. But there are people like, if you look at works of Cato and so on, there are people who do such things. Yeah, or equivalent K theory. There are all kinds of constructions which give you these things. Right. As I said, I'm not the right person to ask that question. Okay. Oops, that's right.
For the question.